Special guest speaker, Professor Robert Wallace from the Department of Material Science and Engineering at the University of Texas at Dallas will be visiting the School of Chemical, Biological, and Environmental Engineering at Oregon State University on September 3rd to talk about 2D materials for nanoelectronics. Research in the Wallace group focuses on the study of surfaces and interfaces, particularly with application to electronic materials and the resultant devices fabricated from them. Current interests include material system leading to concepts that may enable further scaling of integrated circuit technology and beyond CMOS-based logic. These include the study of the surfaces and interfaces of compound semiconductor systems, including arsenides, nitride, phosphide, as well as antimonides, and most recently 2D materials such as graphene and transition metal dichalcogenide. Professor Wallace has authored or co-authored over 400 publications in peer-reviewed journals and proceedings with over 25,000 citations according to Scopus and over 35,000 citations according to Google Scholar. Dr. Robert Wallace is also an inventor on 45 US and 27 international patents and a co-inventor of the hafnium-based high-K gate dielectric materials now used by the semiconductor industry for advanced high-performance logic in microprocessors. He was named Fellow of the AVS in 2007. Professor Wallace will be talking about 2D materials for nanoelectronics, prospect and integration challenges. So the size reduction and economics of integrated circuits captured since the 1960s in the form of Moore's law is under serious challenge. Current industry roadmaps reveal that physical limitations include reaching aspect associated with truly atomic dimensions, and the cost of manufacturing is increasing such that only 2 or 3 companies can afford leading-edge capabilities to address some of the convention's materials physical limitation. 2D materials such as graphene, phosphorene, hexagonal boron nitride, and transition metal dichalcogenide have captured the imagination of the research community for advanced application in nanoelectronics, optoelectronics, and other applications. Among 2D materials beyond graphene, some exhibit semiconducting behavior such as transition metal dichalcogenide (TMDs) and present useful bandgap properties for application even at the single atomic level. In addition to the potentially useful band gaps at the monolayer thickness scale, the atomically thin layers should enable through electric field penetration through the channel, thus enabling superior electrostatic control. Further, with such thin layers, the integration with suitable gate dielectrics can result in mobility enhancement. Applications beyond CMOS are also under exploration. From an interface perspective, the ideal TMD material may be expected to have a dearth of dangling bonds on the surface interface, resulting in low interface state densities, which are essential to efficient carrier transport. The ideal TMD materials have much appeal, but the reality of significant density of defects and impurities will surely compromise the intrinsic performance of such device technologies. This presentation will examine the state of the art of these materials in view of the research on semiconductor device application and the challenges and opportunities they present for electronic and optoelectronic application. Professor Wallace's research was supported in part by the Semiconductor Research Corporation (SRC), New Limit Center, and NIST through an award, and by the Eric Johnson Distinguished Chair at the University of Texas at Dallas.